Hello everyone. Today we are going to learn Fourier Transform Infrared Spectroscopy. So this is an important technique in nanomaterial calibration. In today's lecture, we are going to learn what is infrared radiation and what is the working principle of FTIR spectroscopy, and we are also going to learn the parts of FTIR spectroscope. At the end of the lecture, we will also have a practical demonstration to understand this technique more in detail. Let us see what is infrared radiation. Infrared radiation is a form of electromagnetic radiation with wavelength longer than visible light but shorter than microwave. And this IR is categorized into three regions: near infrared, mid infrared and far infrared. And this mid infrared region is very important in spectroscopy because it corresponds to vibrational energies of molecular bonds, and the mid infrared region is ranging between 400 to 4000. Let us briefly see the history of FTIR. The infrared light was discovered in the early 19th century, and the first commercial FTIR spectrometer was introduced in 1967. So, due to the advancement in the technology, the DSP and ATR technique significantly improved the speed and accuracy of FTIR analysis. And currently, this FTIR analysis is an important characterization technique across fields like pharmaceuticals, biotechnology and material science. Let us see what is Fourier Transform Infrared Spectroscopy. The FTIR is a technique used to analyze the interaction of infrared light with a sample. It helps in identifying chemical bonds in a molecule by measuring their vibrational frequencies. And this IR spectrum of a molecule acts like a molecular fingerprint. How we have different fingerprints, similarly the IR spectrum of molecules act like a molecular fingerprints, and it provides a detailed information about the sample's chemical structure and composition. And this FTIR is commonly used in material science, pharmaceuticals and nanomaterial analysis for identifying functional groups, studying the molecular structures and analyzing the complex mixtures. Let us see the principle. Here the molecules observe IR radiation when the frequency of the radiation matches the natural vibration frequency of their bonds. The vibration occurs in two primary ways: one is stretching, the other one is bending. Stretching means changes in the bond length, and the stretching can be divided into two types. One is symmetric stretching, that means bonds stretch or compress simultaneously. The other one is asymmetric stretching, one bond stretches while another compresses. Under the bending, there are several types including scissoring, rocking and wagging and twisting. So, the bending means it is a changes in the bond angle. For a molecule to observe IR radiation, it must be IR active. The vibration must cause a change in the molecule's dipole moment. So, then only we can measure the spectrum, and each molecular bond observes IR at characteristic frequencies, creating a distinct fingerprint spectrum for the sample. From this tabular column, you can get a clear idea about the molecular vibrations of various molecules and their corresponding peak position. For example, if it is a amine, you get NH stretch and the peak position will be between 3550 to 3250. Similarly, for other molecules also, we can understand from this table what kind of vibration we get and where the peak position will be in the FTIR. Let us learn about the parts of FTIR instrument. The first one is IR source, and we can use silicon carbide or zirconium oxide. And the next one is interferometer. The interferometer is the main component of an FTIR spectrophotometer. It includes three key parts. One is a beam splitter, and other one is a stationary mirror, and the next one is movable mirror. The beam splitter divides the incoming light beam into two parts. One part goes to the moving mirror and the other part reflects to the stationary mirror, and both the mirrors reflect the light back to the beam splitter. Then the beam splitter recombines the two beams and sends them through the sample chamber. Then from the sample chamber it goes to the detector. So, here the sample holder, it holds the sample for analysis. The sample holder can be for liquid cells, solid holders for if you are using KBR pellets, and we can also use the ATR crystals if you are using the ATR FTIR. And we have the detector. The detector converts the transmitted or reflected IR radiation into electrical signals, and the electrical signals are processed by the computer for analysis. Let us see the working of FTIR spectroscopy in detail. The FTIR instrument emits infrared radiation from a broadband source. Then the IR beam is directed to a beam splitter, which divides the beam into two paths. One beam is directed to a moving mirror, while the other is directed to a stationary mirror, as I told you in the previous slide. Then the beam recombines at the beam splitter to create an interferogram. Then the combined IR beam passes through or reflects off the sample, where it interacts with the sample's molecules, causing them to absorb specific IR frequencies. Then the transmitted or reflected IR light is detected by a detector, which converts it into an electrical signal. Then the interferogram is processed by a Fourier transform to convert the time domain data into frequency domain spectrum. Then the software generates the FTIR spectrum, which displays the absorption of IR light at various wavelengths corresponding to the molecular vibration in the sample. Then the resulting spectrum is analyzed to identify the functional groups, chemical bonds and molecular structures in the sample. When compared to the traditional FTIR, most of the labs nowadays they are using the ATR-FTIR. Let us see what is ATR-FTIR. ATR means attenuated total reflectance, and this is the most commonly used sampling technique in FTIR spectroscopy. The ATR is based on total internal reflection and evanescent wave. So, the TIR means when a light travels from a denser medium to a less dense medium at an angle greater than the critical angle, it undergoes total internal reflection. And let us see what is evanescent wave. While undergoing the total internal reflection, a portion of the electromagnetic wave penetrates slightly into the second medium, that is your sample. This wave is evanescent wave, and the evanescent wave does not propagate, and it also decays exponentially with distance from the interface. From this animation you can understand, when you apply the IR light to the sample, evanescent wave is created and that can be detected by the detector. In the ATR-FTIR, evanescent waves are crucial, whereas the IR beam undergoes total internal reflection within an ATR crystal. The ATR crystal can be a diamond or zinc selenide. At each reflection point, an evanescent wave penetrates a short distance into the sample in contact with the crystal. The sample absorbs specific IR frequencies based on its molecular vibration, modifying the evanescent wave. The altered wave returns to the detector, where it is processed to generate the IR spectrum. ATR-FTIR gained its popularity due to its ability to quickly and easily measure a broad range of sample, including liquids, solids, powders, semi-solids and paste. In the traditional FTIR, we have to use the potassium bromide for preparing the sample. Let us see the importance of potassium bromide in FTIR. The potassium bromide is an essential part of the sample preparation for FTIR. It serves as a carrier for powdered samples. It is highly transparent to infrared light, which is crucial for FTIR analysis, and it does not absorb the IR radiation in the mid IR range. And due to a homogeneous mixing of sample with KBr, the chances of heterogeneous absorption are minimized. And the KBr pellet also helps to protect the sample from oxidation, contamination and moisture absorption during the FTIR analysis. And it also helps to get the consistent and accurate FTIR measurements. Let us see the difference between traditional FTIR and ATR-FTIR. The first one is sample preparation. Traditional FTIR often require extensive sample preparation. We have to use KBr pellets, whereas in ATR-FTIR the sample preparation is very minimal. There is no need for KBr pellets, and in case of IR interaction, the IR beam passes through the sample directly. In ATIR, the IR beam interacts with the sample through an ATR crystal, with the evanescent wave penetrating the sample surface, as I told earlier. And in case of sample thickness, we have to use thin sample in the traditional FTIR to allow the IR light to pass through. But in case of ATR-FTIR, it works for sample for various thickness. The measurement principle for the traditional FTIR is it measures the absorption of IR radiation as it passes through the sample, whereas in case of ATR-FTIR, it measures the absorption of IR radiation by the evanescent wave at the sample surface. And the traditional FTIR measures bulk properties of the sample, and ATR-FTIR primarily sensitive to the surface of the sample. So, that is why it is make it ideal for thin films and coatings. And in the case of traditional FTIR and ATR-FTIR, the data quality is almost similar, and the traditional FTIR provides high quality data for bulk material analysis. In ATR-FTIR, it provides the accurate surface level data, and that may not reflect the bulk properties. Let us see some of the important applications of FTIR. So, we can use the FTIR for understanding the surface functionalization of the nanoparticle. For example, we can identify the functional groups on the nanoparticle surface. For example, if you are coating the nanoparticle with the PEG, polyethylene glycol, you will have the functional group like OH, and if you are coating the nanoparticle with polyethylamine, so you get the amino group. So, we can use the FTIR for understanding the functional groups present on the nanoparticle surface, and we can also use it for characterization of carbon based nanomaterials. For example, analyzing the functionalization and structural changes in the graphene, carbon nanotubes and their derivatives. For example, whenever you are functionalizing the graphene or carbon nanotubes, we can compare the carbon nanotubes with the functionalized carbon nanotubes, and we can identify the changes in the carbon nanotubes after adding the functional group. And this can be also useful for evaluating the cross linking and the chemical modification in the hydrogels or nanogels. So, before cross linking and after cross linking, what kind of chemical modification happened in the hydrogels. So, that can be analyzed using the FTIR, and this FTIR can also be useful for understanding the thin films and nano coatings. So, it will determine the chemical composition and bonding in the nanostructure coatings, which we are mainly using for electronics and optics application. And this can be also useful for nano carrier drug delivery system. So, it will be useful to confirm the drug encapsulation and also the bonding interaction and release mechanism in the nano carriers. For example, if the drug is encapsulated inside the nanoparticle, so we can measure the chemical modification and the structure modification using the FTIR. So, this will give a different kind of peak, and in some cases if the drug is attached on the surface, so that will give a different kind of FTIR peak when compared to the drug is inside the nanoparticle. So, based on that we can understand whether the drug is encapsulated or it is attached on the surface by using this FTIR spectroscopy. And this can be also useful for photocatalyst and energy nanomaterials for studying the surface chemistry of nanomaterials in photocatalysis and fuel cells and batteries. We can also use it for environmental applications. For example, we can use it for analyzing the functionalized nanomaterials for pollutant removal and environmental monitoring. So, these are the various applications of FTIR. Let us see some of the common issues which we face when we do the FTIR spectroscopy and how to overcome that. The first issue is low signal intensity. It may be due to the weak sample concentration or the sample is too thick or not properly aligned. Ensure that you have the sufficient sample concentration and use thinner samples, and also check the alignment of the sample in the beam path. And the next issue is poor resolution or noisy spectra. It may be due to the insufficient signal to noise ratio or the poor detector performance or noisy environment. So, this can be overcome by increasing the number of scans to reduce the noise ratio and minimize the environmental vibration and ensure proper calibration. And third issue may be interference from water or carbon dioxide. So, to overcome that, what we have to do is we have to use the desiccator to remove the moisture from the sample before measurement. And the other issue is baseline drift or fluctuations. So, it may be due to the temperature instability or misalignment of optics. This can be overcome by calibrating the instrument before the measurement. And if you are getting incorrect or overlapping peaks, it may be due to the sample contamination or it may be due to the inappropriate sample preparation. So, always make sure that you are using the clean equipment and adjust the sample amount to avoid the saturation. And the last one is absorption by KBR pellet. So, the possible cause may be due to the contamination or moisture in the KBR pellet. So, this can be overcome by using the dry KBR pellet, by drying the KBR pellet before the use and properly mix the sample, and always prepare the fresh pellets. I hope you got the overall idea about the FTIR spectroscopy. Let us go to lab and learn this technique more in detail. Today we are going to perform FTIR analysis for L16. First we have to make a KBr pellet. So we will take KBr powder and L16 powder to maintain a ratio of 1:100 of sample to KBr. We have to grind these two powders together to make a fine homogeneous powder. Now to make the KBr pellet, first clean the parts of the KBr pelletizer using tissue paper. Arrange the parts of the pelletizer as shown in this video. After the assembly of the pelletizer, add a few scoops of the prepared sample mixture. Tap the assembly few times to settle all the powder on the base of the pelletizer. Now insert the other parts of the pelletizer from the top. Keep the pelletizer in the machine to apply the pressure on the pelletizer. The pressure is currently 0, so we will first close the pressure valve and then use the handle to increase the pressure in the pelletizer, which will convert the powder into pellet. Apply a pressure on the pelletizer. Once it is done, first release the pressure using the pressure valve. You can see that the pressure has gone down to 0. Now loosen up the screw and take out the pelletizer. Take out the rod first and then remove the lower part of the pelletizer carefully. Take out the pellet carefully using a forceps with a sharp pointed end. Now you can see the pellet. Store the pellet in a tissue paper to avoid moisture. Coming on to the software part of the FTIR analysis, the machine has been set to take transmittance data in the wave number range from 4000 to 400. First we have to collect the background without the KBr pellet. So ensure that the sample holder is clean and then take the background. It will start collecting the background. After it has collected the background, keep the pellet in the pellet holder carefully without breaking it as shown in this video. Keep this sample holder in the machine carefully. Close the cover. Now press next to take the FTIR measurement. The sampling is going on. On the screen, you can see the FTIR measurement for the L16 sample with all its characteristic peaks. Now save the file with the desired name and location. Click Done and exit the software. Take out the sample from the FTIR machine and turn off the machine. This FTIR spectrum of L16 shows the characteristic vibrational modes of functional groups present in the molecule. Amine stretching highlighted in pink color. So this peak corresponds to the stretching vibration of the primary amine group in the L16. It indicates the presence of an amino group. Then thiol stretching highlighted in green. So this peak represents the stretching vibration of the thiol group, a unique feature of cysteine. The intensity and the peak position of this may vary depending on the environment of the thiol group. So the next one is carboxyl group highlighted in purple. So this peak corresponds to the symmetric and asymmetric stretching vibrations of the carboxylate group. It confirms the carboxylic acid functionality deprotonated to form the carboxylate group. The high transmittant values indicate strong absorption in specific regions where functional groups vibrate at characteristic frequencies. The presence of distinct peaks in the pink, green and purple areas confirms the characteristic groups amine, thiol and carboxyl, essential for understanding the structural integrity of L16. As a summary, in today's lecture we learnt what is infrared radiation and what is the working principle of FTIR spectroscopy, and also what are the various parts of FTIR spectroscopy, and through practical demonstration we also learned this FTIR spectroscopy in detail. Thank you everyone for your kind attention. I will see you in another interesting lecture.